Today we're going to talk about special angles. A special angle is one that you can find the sine, the cosine, or the tangent of without using a calculator or a chart. I'm going to show you how to do that with a couple of different triangles so that we can find the special angle, sine, cosine, tan for certain angles today. We're going to start with an equilateral triangle, and so our equilateral triangle has all three sides equal and all three angles equal, and each of those angles is 60 degrees. If I take that triangle and I cut it in half right down the center like this, then I'm going to get a right angle triangle that looks like the one I've got drawn on the right. We can fill in some information. We know that if the bottom angle is 60 and we have a right angle of 90 degrees in the corner, then this angle must be 30 degrees up here. But we don't know much about the side lengths, and if we did, it would really help us to be able to find our trig ratios for these angles. So let's assign a length for the hypotenuse. I'm going to let this side be 2 units in length. If I cut this triangle into two exact halves, then that means that each of these halves would be half of 2 or 1 unit in length. Now, I don't know the perpendicular side, this altitude of the triangle, but I do know Pythagorean theorem, and Pythagorean theorem will let me work out the length of that side. I know that a squared plus b squared equals c squared. So if I'm trying to find a short side, which I am in this case, then I'm just going to take c squared minus the other short side. So in that case, I've got a squared equals 2 squared minus 1 squared or a squared equals 4 minus 1. So a squared is 3, which means a must be the square root of 3. And we're going to stop there. We're not going to go to the calculator and find out the square root of 3, because as soon as we do that, 3 is an irrational number. The square root of 3 is an irrational number, and that means it's going to have a never-ending string of decimals that never round off and never repeat. So we can never get an exact value for the square root of 3. You see where we're going here in terms of exact values of trig values. So if I know that that side is root 3, then I have all three sides of my triangle and all three angles of my triangle, and I could find any trig ratio that I needed. So if I wanted to find the sine of 30 degrees, and I know that this side is 2, this side is 1, and this side is root 3, because these sides will always be in the same ratio, it doesn't matter what those numbers are, then sine of 30 is opposite over hypotenuse, according to SOHCAHTOA, and opposite over hypotenuse is 1 over 2. So sine of 30 is 1/2, or 0.5. The cosine of 30 is adjacent over hypotenuse, and so in that case we're going to have root 3 over 2. And that's the exact value for the cosine of 30. If you press cosine of 30 on your calculator, you're going to get 0.8660 and then a whole bunch of decimal places after that. So as soon as you round it off, you are no longer giving the exact value of the cosine of 30. If we leave it as root 3 over 2, we have the exact value because nothing has been rounded off. So tan of 30, tan is opposite over adjacent, and so tan of 30 is going to be 1 over root 3. Now, normally we would rationalize that denominator, which means we multiply by root 3 over root 3 so that we don't have a radical in the denominator. We won't bother to do that here today. For sine of 60, opposite over hypotenuse again. So this time, the opposite side becomes the root 3. We have root 3 over 2. For cos of 60, we have adjacent over hypotenuse 1 over 2. And for tan of 60, we have root 3 over 1. So those are all exact values for the sine, the cosine, and the tan of 30 degrees and 60 degrees, so that no rounding off is necessary. If we think about another type of triangle, if we think about the isosceles triangle that has 90 degrees and 245 degrees, then we can also use a similar approach to find the exact value of the sine, the cos, the tan of 45 degrees. So if I'm looking at an isosceles triangle and I decide to assign the length of the two equal sides to 1 unit each, then using Pythagorean theorem, I can find c squared equals 1 squared plus 1 squared, or c squared equals 2, meaning that c equals root 2. So I have a 45, 45, 90 triangle with sides of 1, 1, and root 2. That means that I can now find the exact value of the sine of 45, which is opposite over hypotenuse, in this case 1 over root 2. For cosine, cosine is adjacent over hypotenuse, but because the opposite and the adjacent sides are the same in an isosceles triangle, then I'm also going to get 1 over root 2. And for tan, tan is really slope, and so that's really rise over run, or opposite over adjacent, and that's 1 over 1, which equals 1. Now, a lot of times you'll see sine and cosine of 45 written as root 2 over 2. You can use your calculators to verify that that's exactly the same thing. What they've done is they've used a process called rationalizing the denominator, because it's not good math form to leave a radical in the denominator of a fraction. If you need help with this topic or any other math topic to help you in a course at Trent, please email me at mathhelp@trentu.ca for an online or an in-person appointment.